6 Easy Pieces by Richard P. Feynman is a collection of 6 foundational lectures that introduce some of the most critical concepts in physics. This book serves as an accessible entry point for anyone interested in understanding the basics of physics, whether they are students, enthusiasts, or just curious minds. The primary purpose of 6 Easy Pieces is to break down complex physical principles into simple, understandable segments. Feynman, a Nobel Prize-winning physicist, was known for his exceptional ability to explain intricate scientific concepts in a way that was both engaging and enlightening. This book captures that essence, making challenging topics accessible to a broad audience. Richard P. Feynman was not only a brilliant physicist, but also a captivating teacher and storyteller. He made significant contributions to the field of quantum mechanics, particularly in the development of quantum electrodynamics, for which he received the Nobel Prize in Physics in 1965. Beyond his technical achievements, Feynman was renowned for his colorful personality, sense of humor, and unique approach to teaching. His ability to demystify science and make it interesting is one of the reasons 6 Easy Pieces remains a beloved and influential work. Feynman's teaching style and its impact on learners. Feynman's teaching style was characterized by clarity, simplicity, and a deep passion for the subject matter. He had a knack for using everyday analogies and thought experiments to illustrate complex ideas, making them more relatable and easier to grasp. His enthusiasm for physics was infectious, inspiring countless students and readers to explore the wonders of the physical world. In 6 Easy Pieces, Feynman distills his lectures into bite-sized, digestible pieces that build a strong foundation in physics. Each lecture is designed to stand on its own, yet collectively they provide a comprehensive overview of fundamental concepts. The importance of understanding fundamental physics. Understanding the basics of physics is crucial because it provides a foundation for all other sciences. Physics explores the fundamental laws that govern the universe, from the behavior of subatomic particles to the motion of galaxies. By grasping these principles, readers can better appreciate how the world works and how different scientific disciplines interconnect. 6 Easy Pieces covers a range of essential topics, including the nature of atoms, the principles of energy conservation, the laws of motion, the theory of gravitation, and the basics of quantum mechanics. These topics form the building blocks of our understanding of the physical universe. The journey ahead. As you dive into 6 Easy Pieces, you'll embark on a journey through the fascinating world of physics. Feynman will guide you step by step, using his signature style to make complex ideas clear and engaging. Whether you're new to physics or looking to refresh your knowledge, this book offers valuable insights and a deeper appreciation for the beauty and intricacy of the natural world. Chapter 1: Atoms in Motion. Atomic Structure. Atoms are incredibly small, much too tiny to be seen with the naked eye. Each atom consists of a nucleus made up of protons and neutrons, surrounded by a cloud of electrons. Protons carry a positive charge, electrons carry a negative charge, and neutrons are neutral. The number of protons in the nucleus determines the element to which the atom belongs, while the arrangement of electrons affects the atom's chemical properties and behavior. Behavior of atoms. Atoms are not static, they are always in motion. The motion of atoms depends on the state of matter they are in. In solids, atoms are closely packed and vibrate in place. In liquids, atoms are more loosely packed and can move around each other, allowing the liquid to flow. In gases, atoms are widely spaced and move freely at high speeds. The motion of atoms is influenced by temperature. As temperature increases, atoms move faster. Feynman emphasizes that the behavior of atoms can explain many properties of matter. For example, the hardness of a solid is due to the fixed positions of its atoms, while the ability of a liquid to flow is because its atoms can slide past each other. The high speed and free movement of gas atoms explain why gases can expand to fill any container. Implications of atomic theory. The atomic hypothesis has far-reaching implications for our understanding of the natural world. By understanding atomic structure and behavior, scientists can explain and predict a wide range of phenomena, from the behavior of materials to chemical reactions. For instance, the atomic theory helps us understand why certain substances are good conductors of electricity while others are insulators, and why some materials expand when heated while others contract. One of the key insights of atomic theory is the concept of conservation of matter. According to this principle, the total amount of matter in a closed system remains constant, even though it may change form. This means that in any chemical reaction, the number of atoms remains the same before and after the reaction, although they may be rearranged to form different molecules. Real-world applications. Feynman provides examples of how the atomic hypothesis applies to real-world situations. For example, the principles of atomic motion explain why heating a metal causes it to expand. When metal is heated, the atoms vibrate more vigorously, pushing each other further apart and causing the metal to increase in size. Another application is in understanding the behavior of gases. The kinetic theory of gases, which is based on the idea of atoms in motion, explains why gases exert pressure on the walls of a container. As gas atoms move rapidly and collide with the container walls, they exert a force, which we perceive as pressure. This theory also explains why the pressure of a gas increases with temperature. As the temperature rises, atoms move faster and collide with the walls more forcefully. Chapter 2, Basic Physics. Conservation of energy. One of the most crucial principles in physics is the conservation of energy. This principle states that energy cannot be created or destroyed. It can only be transformed from one form to another. In other words, the total amount of energy in a closed system remains constant over time. Feynman explains that energy can take various forms, such as kinetic energy, the energy of motion, potential energy, energy stored due to an object's position, thermal energy, heat, and chemical energy, stored in chemical bonds. An example of energy conservation in action is a pendulum. As the pendulum swings, its energy constantly shifts between kinetic energy, when it's moving fastest at the lowest point, and potential energy, when it's momentarily at rest at the highest points. Despite these changes, the total energy of the pendulum system remains the same. Laws of motion. Feynman introduces Newton's 3 laws of motion, which are fundamental to understanding how objects move and interact. First law: inertia. An object at rest will stay at rest, and an object in motion will stay in motion, unless acted upon by an external force. This law highlights the concept of inertia, the tendency of an object to resist changes in its state of motion. Second law: force and acceleration. The acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Mathematically, this is expressed as backslash F equals ma backslash, where backslash F backslash is the force, backslash m backslash is the mass, and backslash a backslash is the acceleration. This law explains how the motion of an object changes when a force is applied. Third law: action and reaction. For every action, there is an equal and opposite reaction. This law means that forces always come in pairs. When one object exerts a force on another, the second object exerts an equal and opposite force back on the first object. This principle is observed in various scenarios, such as the recoil of a gun when fired or the propulsion of a rocket. Understanding forces. Feynman discusses the different types of forces that can act on objects. These include gravitational force, the force of attraction between two masses. This force is responsible for keeping planets in orbit around the sun and objects falling to the ground. Electromagnetic force, the force between charged particles. This force is responsible for phenomena such as electricity, magnetism, and light. Normal force, the force exerted by a surface perpendicular to an object in contact with it. This force prevents objects from passing through solid surfaces and is what you feel when you push against a wall. Frictional force, the force that opposes the relative motion of two surfaces in contact. Friction is what slows down and eventually stops a moving object. It is essential for activities like walking and driving, as it provides the necessary grip. Applications of basic physics principles. Feynman provides examples of how these fundamental principles apply to everyday life and various scientific fields. Engineering, understanding forces and energy conservation is crucial for designing structures, vehicles, and machines. Engineers use these principles to ensure that buildings are stable, bridges can support their weight, and engines operate efficiently. Medicine, physics principles are applied in medical technologies such as imaging techniques, X-rays, MRI, and radiation therapy. These technologies rely on the behavior of electromagnetic waves and particles to diagnose and treat medical conditions. Environmental science, conservation of energy, is a key concept in studying ecosystems and natural processes. Scientists use this principle to understand the flow of energy through food chains, the impact of human activities on the environment, and the development of sustainable technologies. Chapter 3. The relation of physics to other sciences. Physics and chemistry. The relationship between physics and chemistry is profound. Chemistry is essentially the study of the interactions between atoms and molecules which are governed by the principles of physics. For example, atomic structure. Chemistry relies on the understanding of atomic structure, which is rooted in quantum mechanics. The arrangement of electrons around the nucleus, the formation of chemical bonds, and the behavior of elements on the periodic table can all be explained through quantum physics. Chemical reactions, the principles of thermodynamics and kinetics, both of which are derived from physics, play a crucial role in understanding chemical reactions. These principles help chemists predict how reactions will proceed, their energy changes, and the rates at which they occur. Physics and biology. Physics also has significant implications for biology. Biological processes are governed by the same physical laws that apply to inanimate matter. For example, molecular biology, the structure and function of DNA, proteins, and other biological molecules are studied using techniques rooted in physics, such as X-ray crystallography and nuclear magnetic resonance, NMR, spectroscopy. Biophysics. This interdisciplinary field applies the principles of physics to understand the mechanics and dynamics of biological systems. Topics such as cellular mechanics, neural signaling, and muscle contraction are explored through the lens of physics. Physics and astronomy. Astronomy is closely tied to physics as it seeks to understand the universe and its celestial bodies. Key connections include gravitation. Newton's law of universal gravitation and Einstein's theory of general relativity are fundamental to understanding the motion of planets, stars, and galaxies. These principles explain phenomena such as planetary orbits, black holes, and the expansion of the universe. Electromagnetic spectrum. Astronomers study celestial objects using different wavelengths of light, from radio waves to gamma rays. The principles of optics and electromagnetic theory, which are rooted in physics, are essential for interpreting astronomical observations. Physics and geology. Physics plays a crucial role in geology, the study of the Earth and its processes. Key areas of overlap include seismology. The study of earthquakes and seismic waves relies on the principles of wave mechanics. Seismologists use these principles to understand the Earth's interior and the behavior of tectonic plates. Geophysics. This field applies physical methods to study the Earth's structure and composition. Techniques such as gravimetry, magnetometry, and remote sensing are used to explore geological formations and natural resources. Physics and psychology. Even psychology, the study of the human mind and behavior, has connections to physics. For example, neuroscience, the study of neural activity and brain function, involves understanding the electrical and chemical processes that occur within neurons. These processes are governed by the principles of electromagnetism and thermodynamics. Cognitive science. Research in areas such as perception, decision-making, and memory often incorporates concepts from physics, such as information theory and signal processing. Feynman emphasizes that physics provides a unifying framework for understanding the natural world. By uncovering the fundamental laws that govern matter and energy, physics lays the groundwork for other scientific disciplines to build upon. This interconnectedness highlights the importance of interdisciplinary collaboration and the value of a solid foundation in physics for all scientists. Chapter 4. Conservation of Energy. Different forms of energy. Feynman explains that energy comes in many different forms, each with unique characteristics. Some of the main forms of energy include gravitational potential energy. This is the energy an object possesses due to its position in a gravitational field. For example, an apple hanging from a tree has gravitational potential energy because of its height above the ground. When the apple falls, this potential energy is converted into kinetic energy. Kinetic energy. This is the energy of motion. Any moving object has kinetic energy, which depends on its mass and speed. The faster an object moves, the more kinetic energy it has. Thermal energy. This is the energy associated with the random motion of atoms and molecules within a substance. The higher the temperature of a substance, the greater its thermal energy. Heat is the transfer of thermal energy from one object to another. Chemical energy. This is the energy stored in the bonds between atoms and molecules. Chemical reactions such as combustion or photosynthesis involve the release or absorption of chemical energy. Nuclear energy. This is the energy stored in the nucleus of an atom. Nuclear reactions such as fission, splitting of a nucleus, or fusion, combining of nuclei, release a tremendous amount of energy. The principle of energy conservation. The principle of energy conservation states that in a closed system, the total amount of energy remains constant over time. Energy cannot be created or destroyed. It can only be transformed from one form to another. This principle is known as the law of conservation of energy. To illustrate this principle, Feynman uses the example of a swinging pendulum. As the pendulum swings, its energy continuously shifts between kinetic energy when it is moving fastest at the lowest point and potential energy when it is momentarily at rest at the highest points. Despite these changes, the total energy of the pendulum system remains the same. Applications of the conservation of energy. Feynman highlights several real-world applications of the conservation of energy, demonstrating its importance across various fields. Engineering. Engineers use the principle of energy conservation to design efficient systems, such as engines, power plants, and renewable energy sources. Understanding how energy is transferred and transformed helps engineers optimize performance and reduce waste. Environmental science. The conservation of energy is crucial for understanding natural processes and ecosystems. For example, the energy flow through food chains in an ecosystem follows the principle of conservation. Energy from the sun is captured by plants through photosynthesis, transferred to herbivores that eat the plants, and then to carnivores that eat the herbivores. Medical technologies such as diagnostic imaging and radiation therapy rely on the conservation of energy. For instance, X-rays and MRIs use electromagnetic energy to create images of the body's internal structures, while radiation therapy uses energy to target and destroy cancer cells. The first law of thermodynamics. The first law of thermodynamics is a specific formulation of the law of conservation of energy applied to thermodynamic systems. It states that the change in the internal energy of a system is equal to the heat added to the system minus the work done by the system. This law is essential for understanding how energy is transferred and transformed in processes such as heating, cooling, and performing mechanical work. Chapter 5. The Theory of Gravitation. Newton's Law of Universal Gravitation. One of the most significant breakthroughs in the history of gravitation was made by Sir Isaac Newton in the 17th century. Newton formulated the law of universal gravitation, which states that every mass in a universe attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This law revolutionized the understanding of motion and provided a unified explanation for both terrestrial and celestial phenomena. It explained why apples fall to the ground, why planets orbit the sun, and why moons orbit planets. Modern understanding of gravitation. Einstein's theory of general relativity. While Newton's law of universal gravitation was groundbreaking, it had limitations and couldn't explain certain phenomena. In the early 20th century, Albert Einstein developed the theory of general relativity, which provided a more comprehensive understanding of gravitation. Einstein proposed that gravity is not a force between masses, but rather a curvature of spacetime caused by the presence of mass and energy. Massive objects like the sun cause space-time to curve, and this curvature affects the motion of other objects. This can be visualized as a heavy object placed on a stretched rubber sheet, causing it to sag and creating a curved surface. General relativity has been confirmed through various experiments and observations, such as the bending of light around massive objects, gravitational lensing, and the precise orbit of Mercury, which couldn't be fully explained by Newtonian mechanics. The role of gravitation in the universe. Gravitation plays a crucial role in shaping the structure and dynamics of the universe. Some of its key effects include planetary orbits. Gravity keeps planets in orbit around stars, such as the Earth orbiting the Sun. The gravitational pull between the Sun and the planets creates stable orbits, which are essential for the existence of life on Earth. Formation of celestial bodies. Gravity is responsible for the formation of stars, planets, and galaxies. It pulls together gas and dust in space, leading to the creation of dense, massive objects that eventually form stars and planets. Tides. The gravitational pull of the Moon and the Sun causes tides on Earth. The changing positions of these celestial bodies lead to variations in the height of ocean tides. Black holes. Extremely massive objects like black holes have such strong gravitational fields that not even light can escape their pull. Black holes are formed when massive stars collapse under their own gravity. Cosmology. Gravity plays a central role in the evolution of the universe. It influences the expansion rate of the universe, the formation of large-scale structures, and the dynamics of cosmic events. Gravitational waves. One of the most exciting discoveries in modern physics is the detection of gravitational waves. Predicted by Einstein's theory of general relativity, gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves travel at the speed of light and can be detected by highly sensitive instruments. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, confirming a key prediction of general relativity and opening a new era of astrophysical research. Chapter 6. Quantum Behavior. Wave-particle duality. One of the central concepts in quantum mechanics is wave-particle duality. Feynman explains that particles, such as electrons and photons, can exhibit both wave-like and particle-like properties. This means that under certain conditions, particles can behave like waves, and under other conditions, they can behave like discrete particles. For example, in the famous double-slit experiment, when electrons are fired at a screen with two slits, they create an interference pattern characteristic of waves. However, when observed individually, they appear as discrete particles. This duality challenges our classical understanding of particles and waves and suggests that the behavior of quantum particles is influenced by observation and measurement. The uncertainty principle. Another fundamental principle of quantum mechanics is Heisenberg's uncertainty principle. This principle states that it is impossible to simultaneously measure certain pairs of properties of a particle, such as its position and momentum, with absolute precision. The more accurately we know one property, the less accurately we can know the other. The uncertainty principle has profound implications for our understanding of the quantum world. It suggests that at a fundamental level, the behavior of particles is inherently probabilistic rather than deterministic. This means that we can only predict the probabilities of different outcomes, not the exact outcomes themselves. Probability amplitudes. To describe the probabilistic nature of quantum mechanics, Feynman introduces the concept of probability amplitudes. In quantum mechanics, the likelihood of a particular outcome is determined by calculating the probability amplitude, which is a complex number. The square of the magnitude of the probability amplitude gives the probability of the outcome. Feynman emphasizes that the calculation of probability amplitudes involves adding them together in certain situations, leading to interference effects. This is analogous to adding wave amplitudes, which can result in constructive or destructive interference. Real-world applications of quantum mechanics. Feynman highlights several real-world applications of quantum mechanics, demonstrating its significance in modern science and technology. Semiconductors and electronics. Quantum mechanics is essential for understanding the behavior of electrons in semiconductors, which are the building blocks of modern electronic devices such as transistors, diodes, and integrated circuits. This knowledge has led to the development of computers, smartphones, and other advanced technologies. Lasers. The principles of quantum mechanics explain the operation of lasers, which produce coherent light through stimulated emission of photons. Lasers have numerous applications, including in communication, medicine, and manufacturing. Quantum computing. Quantum mechanics forms the basis for quantum computing, which leverages the principles of superposition and entanglement to perform calculations more efficiently than classical computers for certain problems. Quantum computers have the potential to revolutionize fields such as cryptography, optimization, and material science. Quantum cryptography. Quantum mechanics enables the development of secure communication methods through quantum cryptography. Techniques such as quantum key distribution ensure that any attempt to eavesdrop on a communication can be detected, providing a high level of security. Medical imaging. Quantum mechanics plays a role in advanced medical imaging techniques such as magnetic resonance imaging, MRI. MRI relies on the behavior of atomic nuclei in a magnetic field to produce detailed images of the body's internal structures.